Hi everybody, welcome to this video on algebra rules with integration. This is our third video in our integration series. To talk a bit about algebra rules for indefinite integration, indefinite integrals and antiderivatives obey the rules of algebra. A little bit of revision here is that when evaluating an indefinite integral, our result is the antiderivative. If you'd like to revise a bit of that material, feel free to have a look at some of my earlier videos. We can use the algebra rules to help us to evaluate integrals for a variety of functions. And we're going to discuss three rules in this video. So our first rule that we're going to discuss is called the constant multiple rule. That's displayed here at the top of the screen. So we can read this as the indefinite integral of some constant k multiplied by a function f of x with respect to x is equal to some constant k multiplied by the indefinite integral of f of x dx. So to think about this a bit and to understand it, if the function that we're integrating contains a constant value which doesn't vary with x, we can move that constant outside of the integral. And we're going to see that here in this example at the bottom half of the screen. So for our example, say we want to evaluate the indefinite integral of 2 pi r with respect to r. Well, our value of 2 pi, that's not going to vary with r. So what we can do is we can treat that as a constant and take it outside of the integral. So if we look at our last line of our slide here, we get that that's equal to 2 pi multiplied by the indefinite integral of r with respect to r. And when we evaluate that antiderivative, we get 2 pi multiplied into, in brackets, r squared over 2 plus c. And when we multiply that out, we get pi r squared because the 2's cancel, and then we get some arbitrary constant c. So looking at that, normally when you multiply 2 pi by a variable c, you get 2 pi c. But our constant of integration is a special case. It represents and stands for some number. And 2 pi multiplied by some number, well, that still gives us some number. So to keep things simple, we simply write plus c, the constant of integration. So that's our constant multiple rule, and that's an example of using it. Now we're going to move on to our next rule. So our next rule is the rule for negatives. It's displayed here at the top of the screen. And we can read it as the indefinite integral of minus f of x dx. That's going to be equal to minus the indefinite integral of f of x with respect to x. So to think about this and to understand it, this is effectively the constant multiple rule that we just looked at, but where the constant k is equal to minus 1. So we can take the constant minus 1 outside of our integral as before evaluating the integral. And we can see that here in an example at the bottom of the screen. So for our example, we want to evaluate the indefinite integral of minus x dx. Well, taking that minus outside of the integral, we get that it's equal to minus the indefinite integral of x dx. And when we evaluate that antiderivative, we get that our result is equal to minus, all in brackets, x squared over 2 plus c. And when we apply that minus sign, we get that our antiderivative is equal to minus x squared over 2 plus c. Now, normally if we applied a minus to some variable c, we get minus c. But again, like we just discussed, that c, that's our constant of integration. It represents some number. And a negative some number, that's still some number. So for simple purposes, we simply write plus c. So before we move on to the third and final rule, we're just going to have a helpful tip with the constant of integration. In our last example, we had that the indefinite integral of minus x dx was equal to minus the indefinite integral of x dx, which was equal to minus the antiderivative, which we got as x squared over 2 plus c, which we then worked out to be minus x squared over 2 plus c. So we could have equally written that evaluates out to, on the next line here, minus x squared over 2 minus c. That would have also been correct. But the key thing to remember is that the constant of integration c, it represents an arbitrary constant. It doesn't matter if it's negative or positive. Its purpose is to represent some possible number. So for this reason, even if our calculations result in a value of minus c, or say some multiple of c, it's correct and simpler to just write c. So that's what we do. And here's an example of that. Say, as before, we wanted to evaluate the indefinite integral of 2 pi r with respect to r. So that's evaluated here on the next line. So we did evaluate this earlier, but the difference here in this line is that we multiply out the 2 pi c to give us 2 pi c. And we don't simplify it down to c, we keep it as 2 pi c. So in this case, 2 pi multiplied by an arbitrary constant c, it's still equivalent to some arbitrary constant c. So because they're the same, for this reason, instead of writing 2 pi c, we simply write c. And this gives us the result that we obtained earlier. 2 pi multiplied by the antiderivative, r squared over 2 plus c. We write that as pi r squared plus c. So moving on to our third rule. This is the sum and difference rule, and it's displayed here at the top of the screen. So we can read this as the indefinite integral of f of x plus or minus g of x with respect to x, that's equal to the indefinite integral of f of x with respect to x plus or minus the indefinite integral of g of x with respect to x. So to think about this rule and to understand it, when we're evaluating an antiderivative of a function that's the sum or the difference of a number of smaller functions like here, we can evaluate the antiderivatives of the smaller functions and then combine them together, and that'll be equal to the antiderivative of the smaller functions combined. To say that in a more formal way, a function is an antiderivative of a sum or difference f plus or minus g if and only if it's the sum or difference of an antiderivative of f and an antiderivative of g. So to understand this a bit more, we're going to see an example now. So here's our example. Say we want to evaluate the indefinite integral of 3x squared minus 4x plus 4 with respect to x. So this is it's a longer integral than we've seen. It's a little bit more complex than we've seen before, but we can use the sum and difference rule to evaluate it. Using that rule, we can evaluate the integral as a combination of smaller integrals. So shown here on our next line, we get that it's equal to the indefinite integral of 3x squared dx minus the indefinite integral of 4x dx plus the indefinite integral of 4 dx. So factoring in those antiderivatives, that's equal to 3 into, in brackets, x cubed over 3 plus an arbitrary constant c1 minus 4 into x squared over 2 plus an arbitrary constant c2 plus 4 into x plus an arbitrary constant c3. And when we multiply out the terms in the brackets, we get x cubed plus c1 minus 2x squared plus c2 plus 4x plus c3. So we've got a number of arbitrary constants there. A combination of arbitrary constants, that's still an arbitrary constant. So we can represent c1 plus c2 plus c3. We can represent all of those as being equal to c, an arbitrary constant. So this gives us the simplified result. Our indefinite integral is equal to x cubed minus 2x squared plus 4x plus c. So here we've started off trying to evaluate an indefinite integral that was more complex and longer than we've seen before, but by using the sum and difference rule, we've been able to do it quite quickly. So in summary, we reviewed some rules of algebra that we can use to make evaluating integrals easier to do. We've covered the constant multiple rule, the rule for negatives, and the sum and difference rule. And we've also reviewed how we can simplify our constant of integration in our results. Thanks a lot for your time. I hope you found this video useful, and see you next video.